Hello, everybody. Welcome to week 16. We are finishing up with chapter 10, liquids and solids. So we are doing 10.4 through 10.6 today. This is all about phase diagrams, the solid state of matter, and lattice structures in crystalline solids. So we're going to jump in with 10.4 phase diagrams. In this, we're going to explain the construction and use of a typical phase diagram, use phase diagrams to identify stable phases at given temperatures and pressures, and to describe phase transitions resulting from changes in these properties, and describe the supercritical fluid phase of matter. So first, I want you to imagine heating or cooling some type of substance. And last section in 10.3, last week, we talked about how during phase changes, the temperature remains constant. So if energy is being absorbed during the phase change, then all this energy is being used to break those intermolecular forces that are keeping the particles close together. So instead of increasing the temperature, it's breaking those IMFs, those intermolecular forces. So that's why our temperature stays constant. Now, if energy is being released during the phase change, then all this released energy is coming from the formation of intermolecular forces, not from the decrease in temperature. So you saw what a heating curve looks like, where we are breaking bonds and energy is being absorbed. But in a cooling curve, it's going to look somewhat like this. It's literally the opposite of a heating curve. Instead, energy is being released during this phase change. So at the far left is where we have our gas, and then we go down to condensation, gas and liquid, liquid, liquid plus solid, and down to solid. So instead of having to add heat, we're taking heat away. Okay. So phase diagrams now, which is what we're going to talk about in this section, look at combining plots of pressure versus temperature for all of the phase transition equilibria of a substance. So we're going to be able to look at one graph to see the physical states of matter under specific temperatures and pressures. So this is an example of what a phase diagram looks like and what's happening at each of the lines. So this is a non-labeled with pressure and temperatures. This is for water. And at these different lines, each solid line is where you have a phase change happening. So the solid line that I just went over is between solid and liquid. So this is where you would have your melting and freezing. So you can look at whatever specific temperature and pressure and figure out, where it's going to melt or freeze. You have then this line here, which is for liquid and gas, and then you have your sublimation deposition for solid gas. We have what's called a triple point here, and this is where you actually have all three phases of matter present at the same time. We also have a critical point, which we'll talk more about later, but what happens here is notice this line stops at the critical point. It doesn't continue here. This actually forms what's called a supercritical fluid, and we will talk about and see an example of that a little later. So let's get into phase diagrams more. Like I said, the solid lines represent phase transitions, so both states of matter are present at the solid lines. The critical point, which is at the end of line BC here, this represents the formation of a supercritical fluid that we're going to talk about later, but these actually have the properties of both gas and liquid, and they're pretty interesting. Sublimation and deposition happen between lines A and B here. And this also, you can see, happens at low pressure and low temperature. So you can see our temperature here is for this sublimation and deposition is below 0.01 degrees Celsius and below 0.6 kilopascals. So very low pressure. But this is actually how food is freeze-dried, is using sublimation. One thing that's interesting for water, so this is for water. Okay, it's not drawn to a constant scale, by the way, because there's some important properties with water's phase diagram that just wants to be underlined here. One of them is that this line between B and D here, which is for liquid and solid, is actually unusual. Notice it has a negative slope. Okay, it's going this way. That's actually not normal. Most substances actually increase their melting point with increasing pressure. But this decrease in melting point with the increase in pressure actually aids in how glaciers move. Okay, so yeah, so most substances do this instead of what water does. And then all three phases of matter, like I said, are here and present at the triple point. So here's a picture of some freeze-dried ice cream. I know a lot of us, when I was a kid, I always wanted astronaut ice cream. I never had it, but from what I've heard, it's not that good. But they go below the triple point. Okay, so remember the triple point, all three phases, we go below that, and we can get into that sublimation area on the line, and we can freeze dry. So here's actually a video I love to show my students. This is from a company that does like they do, oh gosh, what do you call it? A lot of emergency aid food. So this is doing a quick time lapse of different foods reacting to the freeze drying process. So you have your fruits and vegetables in the top two, gummy worms in the third, and then that's orange juice on the very bottom. So what's actually happening there, and the reason that the stuff puffs up is actually because you start by freezing everything just to get the water that's in it frozen solid. And then when you put it in the oven, the freeze drying oven, if you want to call it that, with that low pressure and temperature, the solid water sublimates into a gas, and in the process of escaping from whatever it is it's in, for instance, those gummy worms, it has to make its way out. So the gummy worms end up puffing up from the gases leaving it, from that water vapor leaving. Whoops. And trust me, it's very easy to get sucked into watching freeze drying time lapses. I highly recommend it. Like I was talking about the pressure with the water curve between liquid and solid helps with how glaciers move. So there's partial melting, which ends up making a layer of water, giving lubrication to assist against glacial movement. So it gives a little bit of water, and the glaciers are able to kind of glide along the surface. So this is a phase diagram for carbon dioxide. This one's a little bit more accurate than the water one we were looking at. And one thing to just be aware of is the y-axis, where the pressure is in a logarithmic scale. So it's not, each tick isn't just 1 kilopascal, it's going up by a factor of 10. So we go 10, 100, 1000, 10,000. So something that might look like a linear plot here actually isn't linear. Logarithmic plots can be kind of weird, but just something to be aware of if you're trying to estimate a number off of this. For instance, if you're looking like halfway through 1,000 and 10,000, that would not represent 4,500. Okay. Generally, these have kind of large spaces that then get smaller and smaller as you get closer. So it's not that easy to estimate with the logarithmic scale. This next video is showing the triple point of water, and this is at 4 times the normal speed. Actually, I'm going to speed it up just a little bit more for the sake of time. Playback speed, let's put it at 1.5. So right now they're lowering the pressure into the system. You can see it already kind of starting to bubble, showing some signs of wanting to boil. Okay, you see that bubbling going on. You can see that there's still that ice present and the water, the liquid water. It gets more interesting, I promise. So now we've hit the triple point, and you can see more of those ice crystals that have formed, but we're still boiling, and we also still have that liquid water also present. And now you can literally see it melting, freezing, and boiling all at the same time. It's a lot more interesting here towards the end. So this is what happens at the triple point of a substance. All right, so let's talk supercritical fluids. So this is that area that was labeled SCF here for carbon dioxide. It's supercritical fluid. So these happen at a certain temperature and pressure for different types of matter. You end up blurring that boundary line between liquid and vapor phases. So the matter takes on properties that are in between a gas and liquid. Okay, the point where this happens, where it starts, is called the critical point, and then the matter now has become a supercritical fluid. Some properties of them: they will fill up their entire container as though they were acting like a gas, but they have a higher density than gases. They can be used to dissolve non-volatile solutes, which is actually very helpful in the process of green decaffeination. In the past, decaffeinating things like tea and coffee, compounds like dichloromethane were used, and it's not good for you. It's very toxic. So they would have to make sure that things were washed very well, and that could also affect the flavor. But using supercritical carbon dioxide actually pretty much just removes the caffeine and leaves most of the flavor. Some other properties is they have virtually no surface tension and very low viscosities, which lets them easily move through small openings to remove things like soluble components. And like I said, they are very helpful solvents in different processes like decaffeination. So again, here's the phase diagram for carbon dioxide. And you can see the temperature, which this happens T critical. It's around 25 degrees Celsius. And that pressure is, I would put that around maybe 8,000 kilopascal. So it's not that unheard of to be able to reach that pressure. These pictures here, we're going to actually watch this actual video, is showing liquid carbon dioxide starting just below its critical point. In A, those two, that green and red thing, those are just floaters with different densities to show you what's happening as far as the density goes. And then you hit the supercritical phase in B, and you can see that the green has a lighter density, hence why it's floating, but the red now has a higher density. So it's kind of, the supercritical phase is kind of in between those densities. Once it's cooled, we lower the temperature and pressure below the critical point in both C and D. And then again, those colored floats kind of show our differences in density. So we'll kind of quickly go through the video. This is actually, OpenStax has a link to this in, where's my mouse? In online. But we are going to look at it. Come on. I'm going to increase the playback speed. Let's do 1.75 here. Oops, sorry. Okay, so we're visualizing the densities of liquid, gaseous, and supercritical CO2. Below the critical point, okay, is on the isotherm 28 degrees Celsius. Both phase, liquid and gas phase, coexist. Above the critical point, we hit the supercritical phase. So this is just kind of showing us this plot, density and pressure. And you can see the vapor line, liquid line. So we have this chamber here, and it's got the green and the red floats in it, starting at a temperature of 28 degrees Celsius and a pressure of 69 bar. And you can see vapor and liquid phase that are coexisting here to start with. And you can also see that where the current liquid line is. The density of the vapor phase is 285 kilograms per cubic meter. The liquid is 660, and water, for reference, is 1,000. So our liquid phase is, it's less dense than water, but it's not that much less dense. The green floater has a density of 320 kilograms per cubic meter, and the red has a density of 600. So both of them have a lower density than the liquid CO2. But they are higher in density than the vapor phase. So now they have started to heat up the cell to 32 degrees Celsius with a pressure of 74 bar. And now we're going to speed up the process. And you can see the two phases starting to merge a bit. The liquid phase seems like it's rising. You can see a lot more movement happening in the cell, and you can see the floaters are starting to separate. We are starting to hit that supercritical phase. Now we're getting that difference in densities happening. We've now hit the supercritical phase where the density is 468 kilograms per cubic meter. And you can see the difference based off the floaters. That red floater had that density of 600, so it's sinking, and the green was 320, and you see it floating. So we are now at the supercritical liquid phase happening for carbon dioxide. Oops. Did it again. Didn't even realize I clicked it. So it's kind of, you don't really see much going on in there, but you can see kind of a lot of movement from that supercritical fluid. I thought what's really cool is that density difference. And now they're cooling down the system to go back to those original phases. And it's going to immediately separate into gas and liquid. And then what's happening is the droplets have a similar wavelength to light, which is why all of a sudden it's very opaque. So it's blocking out the light because it has that similar wavelength to it. And now everything is separating, and we are back to where we started. So what's really nice with the supercritical fluid, like for CO2 decaffeination, is after the caffeine has been recovered, it's really easy to get the CO2 back, because all you do is then raise that temperature a little bit, raise your pressure, and you go back to starting conditions, and you can collect your CO2 and go again. So let's look at a quick example. If we shake a carbon dioxide fire extinguisher on a cool day around 18 degrees Celsius, we can hear liquid CO2 sloshing around inside the cylinder. However, the same cylinder appears to contain no liquid on a hot day around 35 degrees Celsius, and we want to explain these observations. So if we were to take into account the phase diagram of CO2, we would notice that on a cool day, 18 degrees Celsius, that is below where the critical point is for carbon dioxide. So it's able to stay present in the cylinder. This is a little bit of a typo here. That should say 18 degrees Celsius. Now, on our hot day, the temperature of the CO2 is greater. Oh, I'm sorry, never mind. That's not a typo. The critical temperature is 31 degrees Celsius or 304 Kelvin. So we're below that temperature at 18 degrees. But on the hot day at 35 degrees Celsius, we're above that critical temperature of 31 degrees Celsius. So we're getting, no matter how high our temperature goes, above this temperature, no amount of pressure can liquefy the carbon dioxide, because now we're in that critical phase. So we can't have any liquid CO2 in the fire extinguisher. So if you were to look at the phase diagram for CO2, okay, so at 35 degrees Celsius, which is right about here-ish, we're past the liquid phase. So it doesn't matter where our pressure is, we're either going to be a gas or a supercritical fluid for the carbon dioxide. Whereas at 18 degrees Celsius, right around here-ish, we can easily be in the liquid range depending on the pressure on that cylinder. So this is just kind of talking about caffeine molecules. Part A is actually the structure of a caffeine molecule. One day I'm probably going to get that tattooed somewhere on my body because I am very dependent on it. And I used to be a Starbucks barista. Double meaning. And it got me through college and grad school. So it has both nonpolar and polar parts to it. So it's soluble in a bunch of different types of solutes. So carbon dioxide being nonpolar, caffeine actually tends to prefer nonpolar solvents. Even though it can dissolve in things like water, it's more soluble in nonpolar solvents. So you put these beans in their extraction vessel and pump in that supercritical carbon dioxide, and it's able to grab onto the caffeine, come up to the top, and then go back into this absorption vessel and leave the system, and the decaf beans now pass through.